It's just after 3:30, and I'll go ahead and begin to move us into this. So I want to welcome all of you that are attending this next installment in our now online Dean's Lecture and Concert series here. And every week is an experiment, and we learn a little bit each week. I can see just from a quick glance that we have faculty, students, alumni, staff, folks from both campuses. So I welcome all of you that have made the time and are taking advantage of this opportunity to connect. I want to echo what I said last week in our first installment of this series that we're winding out this semester with, that I just want to commend again both of our campus communities, students, faculty and staff, and the whole college community, alumni, board members and friends for the energy and the adaptability and resilience and strong sense of community that we've shown through this transition. And we continue to learn and adapt and address the challenges that we face at the college, and of course the challenges that we all face beyond. And for my part, it's encouraging whenever we can do anything that reminds us of the heart of our work here and the substance of our community. And this is one of those moments. I will mention that we will have a talk next week at this same time. Annapolis tutor Rebecca Goldner is going to share some of her reflections on Simone de Beauvoir, and we will have a small group of moderators that will open up a conversation afterwards, and then we'll have a question period. Today, the format will go that in just a moment, I will hand the microphone over to Mr. Fisher. We'll have his lecture. He'll say a couple of things to prepare us for that. At the end of that, we will have a question period, and that will probably combine using the function of hand raising and unmuting individuals from the audience so that you can ask questions in live voice, and also taking some questions through the Q&A box or the chat box. So we'll do that afterwards for as long as folks want, or Mr. Fisher and I can withstand whichever comes first. We have a strong tradition at the college of not introducing our own, and I want to honor that by not giving Mr. Fisher the introduction he would deserve in any other setting. But because this is such an unusual platform and we might have some guests from outside the college community, I do just want to thank and welcome Howard Fisher, one of our senior faculty who surely has been as steeped in and influential in the development of our laboratory and mathematics programs at the college. I'm looking right here on my desk at the beautiful edition of Faraday's Experimental Researches in Electricity that he edited, that's indispensable for us, and he's made many other contributions as well. And I want to note, recently, as we've shifted into this world, he's stepped right in and helped some of our lab tutors come up with really lovely DIY practica that some of our students could do at home. And I just watched today a thank you video that our January freshmen sent to him, playfully but sincerely, for the lovely work he did and helping to guide them towards doing a balance and Barros practica at home. And it seemed like it was a remarkable success. So with that, I thank you, Mr. Fisher, for your willingness to join in this experiment. I guess I should add, if we have any technical problems, we will do our best to address them. Be patient, and we'll just keep moving forward. Mr. Fisher.
Thank you, Walter. And thanks to everyone for joining in today. It's too bad we have to come together through the ether instead of in the Great Hall. But what better medium for a lecture on Maxwell, who gave us the theory of electromagnetic waves in the ether. So just a few words of explanation before we begin. My talk includes slides, videos, and sounds, as well as my own narrative. And I don't have the facilities here at home to combine all of them in real time. So what I did was to pre-record the actual presentation, but afterwards I'll come back on live camera for our question period. Unfortunately, without tea and cookies. So with your permission, let's begin.
James Clerk Maxwell was acclaimed during his lifetime as one of Britain's preeminent mathematicians. And even today, his great treatise on electricity and magnetism continues to anchor Maxwell's standing as the consummate mathematical physicist. So when we turn to the treatise, we may well be astonished to find Maxwell making this extraordinary remark.
Before I began the study of electricity, I resolved to read no mathematics on the subject till I had first read through Faraday's experimental researches in electricity.
That historic recording was discovered only a few months ago and has never before been presented in public. We shall hear more from Maxwell during the course of this talk, so as you take in his warm Scottish burr, keep in mind that the original date of this lecture was to be April 1st. But to return to Maxwell's comment, it is startling to see him display such caution, even suspicion towards mathematics. What are the grounds of this wariness? And what made Faraday's writings a sounder introduction to electrical thinking than those of the mathematical theorists? If only we could look over Maxwell's shoulder as he reads Faraday and see what it is he finds there. Well, to a gratifying extent, we can. For Maxwell conveyed much of his experience as a reader of Faraday in a paper he wrote some 18 years prior to the treatise, the essay titled On Faraday's Lines of Force. Although most of that lengthy paper is expository in character, Maxwell wrote as a reader of Faraday in the first 15 or 16 pages, and it is to those initial pages that I will direct my remarks today. Maxwell read On Faraday's Lines of Force before the Cambridge Philosophical Society at its meetings of December 1855 and February 1856. It was an unusual paper. Then, as today, scientific articles were generally either experimental or theoretical in character. In this paper, though, Maxwell acknowledged that he had, I quote, hardly made a single experiment in electrical science, nor was he, I quote again, attempting to establish any physical theory. Instead, he set out to demonstrate the power and fruitfulness of an imaginative device that had been raised to splendid prominence by Faraday, the line of force. Many of you will have studied these lines of force in the laboratory, and if so, you may have employed this technique. Using a small magnetic compass, you would have recorded the successive positions of the needle while moving the compass always in the direction in which the needle pointed. Perhaps you ended up with a pattern like this one. The compass, then, traces lines of magnetic force, and we can follow lines of electric force with a different kind of pointer. A pivoting length of soda straw shows the radial direction of electric lines of force as they emerge from the dome of a Van de Graaff generator. A map of those radial lines would look like this. With a more sensitive indicator and a lot more patience, we could follow the lines for longer distances. Eventually, of course, they terminate on nearby objects or on the walls of the room. But in the absence of such objects, we can infer that the lines would remain straight and radial to infinity. Maxwell is especially drawn to two aspects of Faraday's lines. First, he argues, despite their merely pictorial appearance, they are just as mathematical as any symbolic equation. To show this, Maxwell devises a method for translating them into quantitative terms. Second, and of even greater importance philosophically, Maxwell finds in Faraday's lines the opening for a new interpretive direction in science, one that Maxwell ratifies with the term speculation. So let me say something about speculation. The term had been used by Faraday to characterize one of his most deeply interpretive essays, the 1852 paper on the physical character of the lines of magnetic force, which some of you may have read in the junior laboratory. Judging by that essay, speculative thought deals with questions so fundamental and consequential, yet so far exceeding our capacity to answer in a rigorous or determinate way, as to hold no obvious place in a context of exact scientific results. But Faraday's paper showed how speculative inquiry could transcend stagnating paradigms and lead to new categories capable of framing scientific phenomena more sensitively than did the traditional views. Nevertheless, Maxwell opens on Faraday's lines of force with the gloomy observation that
the present state of electrical science seems peculiarly unfavorable to speculation.
At the time Maxwell wrote, that state was one that abounded in results which were factually certain, yet systematically fragmentary. Particularly galling to Maxwell was the narrow view of mathematics he found among the professed mathematicians, a group that included many scientists, who recognized no other forms of mathematical thinking than symbolic algebra and calculus. Now, there is no doubt that mathematical formalism bestows great advantages of power and exactitude. But when it is mistakenly regarded as definitive of the science itself, the quantitative impulse may actually interfere with thought. For, Maxwell notes,
the student must make himself familiar with a considerable body of most intricate mathematics, the mere retention of which in the memory materially interferes with further progress.
By no means is Maxwell disparaging mathematics with these remarks, but it seems clear that he regards mathematical proficiency as only instrumental to scientific understanding, not as its core and center. He resolves,
the first process, therefore, in the effectual study of the science must be one of simplification and reduction of the results of previous investigation to a form in which the mind can grasp them.
I want us to take special note of this phrase, a form in which the mind can grasp them. It seems, on the one hand, to single out intelligibility as Maxwell's chief concern. At the same time, he evidently thinks that such intelligibility must be gained by deliberate effort, one involving simplification and reduction. In this, I find his stance markedly different from Faraday's, as I will note later on. Maxwell continues.
The results of this simplification may take the form of a purely mathematical formula or of a physical hypothesis. In the first case, we entirely lose sight of the phenomena to be explained.
Let us take note of Maxwell's first case, the purely mathematical formula. How does such a formula lose sight of the phenomena? A favorite example for Maxwell is the force of attraction between opposite electrical charges. It is an inverse square force. If one of the charges has value Q and the other is unity, that force is expressed F equals Q over R squared. What does this expression lose sight of? Maxwell might say that the formula is blind to the very attraction it sought to elucidate. How, for example, does one charged body manage to draw, for that is the root meaning of attract, another? For that matter, is draw even the right verb? The formula usefully relates the relevant magnitudes, but it affords us scant insight into the action itself. As for the other alternative, Maxwell warns,
If, on the other hand, we adopt a physical hypothesis, we see the phenomena only through a medium and are liable to that blindness to facts and rashness in assumption which a partial explanation encourages.
One such physical hypothesis in electricity is that of two electrical substances, each supposedly endowed with an inherent ability to attract distant portions of the other, or repel distant portions of itself. But although that idea tries to represent attraction as the exercise of a power, thus attempting to correct the blindness of the mere formula, it implicitly ascribes all the action to the hypothetical substance and discounts any role for space. This is the so-called action at a distance doctrine, which holds that the attractive or repulsive power acts directly upon its distant object, without having to be propagated or transmitted by any intervening medium or agency. But in so doing, the hypothesis makes one whole locus of the phenomenon, the space between the bodies, effectively invisible to us. Maxwell is warning us that both these expedients, the mathematical formula and the physical hypothesis, can lead us astray. Yet both spring from the mind's necessary effort to find, as he stated earlier, a form in which it can grasp the truths that are placed before it. Although the world is intelligible, we have to find that intelligibility for ourselves. No being or power, and certainly not nature itself, can find it for us. We need to devote all our cleverness and imagination to the task. But our very determination to satisfy the mind may lead us along paths that display only the air of intelligibility, not the real thing. One such path descends into simplistic formalism. Another indulges our tendency to exalt the merely familiar elements in our experience to the status of essential ones. To escape from these hazards, Maxwell believes,
we must discover some method of investigation which allows the mind at every step to lay hold of a clear physical conception Without being committed to any theory founded on the physical science from which that conception is borrowed, so that it is neither drawn aside from the subject in pursuit of analytical subtleties, nor carried beyond the truth by a favorite hypothesis.
This, I should say, does not seem like easy advice to follow. We are neither to be drawn aside nor carried beyond. It would be bad enough if these errors were the result of outside forces thrust upon us. But our situation is the more distressing in that both these menaces arise from our own felt needs. When we cling to a favorite hypothesis, I suspect it is because we crave something definite to be committed to. When we run after analytical subtleties, it is perhaps because we long for the comparative safety of indifference and abstractness, the very opposite of commitment. In the opening paragraphs of On Faraday's Lines of Force, Maxwell seeks to chart a route between the twin perils, one he believes can protect the kind of imaginative freedom that Faraday cultivated and that Maxwell himself deeply admires. That route is the way of analogy and metaphor. He introduces it in this passage.
In order to obtain physical ideas without adopting a physical theory, we must make ourselves familiar with the existence of physical analogies. By a physical analogy, I mean that partial similarity between the laws of one science and those of another, which makes each of them illustrate the other.
Examples of such analogies are easy to find. The laws of light refraction, for example, resemble the laws of waves in an elastic medium. Their paths also resemble the paths of a stream of particles, though not their velocities. Each of these similarities may tempt us to propose a physical hypothesis, as the first led Huygens and the second led Newton to offer their wave and particle theories of light, respectively. But for Maxwell, such striking similarities are not to be seen as hypotheses in the making. So far from promoting unequivocal doctrines, analogies invite the mind to live in two worlds at once, activating the kind of vision the poet Louis Turco called double-angled. That is true even for what Maxwell styles the most universal of all analogies, the analogy between the properties of nature and the properties of number, the very correspondence which makes mathematical physics possible at all. For that, too, is still only an analogy. It does not in itself imply that algebraic relation either is or should be the paradigm for physical science. Maxwell will construct a physical analogy of his own. Consider again those radial lines of force that originate from the isolated electrified sphere I mentioned earlier. A diagram like this one clearly shows the direction of the force at each point, yet it conveys only a vague notion of the intensity or magnitude of the force. But, Maxwell points out,
if we consider these not as mere lines, but as fine tubes of variable section carrying an incompressible fluid, then, since the velocity of the fluid is inversely as the section of the tube, we may make the velocity vary according to any given law by regulating the section of the tube, and in this way we might represent the intensity of the force as well as its direction by the motion of the fluid in these tubes.
Let us try to follow Maxwell's advice by considering the isolated charged sphere on the left, as though it were a single fluid source immersed in an infinite sea of fluid on the right. And instead of attending to the lines of force that arise from the charged sphere, we shall consider the tubes of fluid flow which arise from the source. Let us then take a closer look at these tubes. Now, the tubes of flow that emerge from a solitary source must necessarily fill the entire space surrounding the source. And in order for this to happen, each tube must expand in cross-section area as it advances. In the expanding tube drawn here, for example, equal volumes of fluid are crossing surfaces A and B. Since the fluid is incompressible, the equal volumes must cross their respective surfaces in equal times. But since the same volume occupies a shorter length where the tube is wider, and a longer stretch where the tube is narrower, the velocities will differ at different points along the tube, inversely as the cross-section varies. Then, if we conceive each line of force emerging from the charged sphere to coincide with the axis of a tube of fluid flow, it is these fluid velocities that will represent the strength of the electric force at each point. But what kind of fluid is this? Maxwell is at pains to emphasize that the field is a purely imaginary one, a fluid in thought.
The substance here treated of must not be assumed to possess any of the properties of ordinary fluids, except those of freedom of motion and resistance to compression. It is not even a hypothetical fluid which is introduced to explain actual phenomena. It is merely a collection of imaginary properties which may be employed for establishing certain theorems in pure mathematics in a way more intelligible to many minds than that in which algebraic symbols alone are used.
The fluid, then, is a device of symbolic thought, no different in that respect from the symbols of analytic mathematics. In the case of our single fluid source, if it emits n units of fluid in unit time, then a total of n tubes of flow, each transmitting fluid at the rate of 1 unit per unit time, will emerge radially from the source, and the source will be said to have a strength of n. Since the tubes have radii for their edges, each one continuously expands in cross-section area, as I mentioned already. Where it intersects a concentric spherical surface having radius r, each tube's cross-section will occupy its share of that surface, that is, 1/nth part of the area of the sphere, 4 pi r squared over n. Unit volume of fluid will therefore occupy a shell having facial area equal to 4 pi r squared over n and some thickness, delta r. That's the blue area in the drawing. Then 4 pi r squared over n times delta r is equal to 1 unit volume, and we write 4 pi r squared delta r over n equals 1, or delta r equals 1 over 4 pi times n over r squared. Since the fluid would have filled up this shell in 1 unit of time, it must have advanced along the distance delta r in that same time. Its velocity is therefore delta r over unit time, which equals 1 over 4 pi times n over r squared. Look, we have an inverse square relation for fluid velocity, one that enticingly calls to mind the inverse square force of electrical attraction, which was F equals Q over r squared. This parallel between the fluid velocity produced by a source having strength n and the electric force produced by a charge Q is Maxwell's physical analogy. How will it enable us to, in Maxwell's earlier phrase, obtain physical ideas without adopting a physical theory? One way is by revealing the existence of shared attributes. For example, there would be no flow at radius r if there were not an uninterrupted connection between the fluid emerging from the source and the fluid that already resides at radius r. The very phenomenon which the quantity v in the upper equation aims to represent cannot be conceived except in relation to a surrounding continuum. In contrast, the force of attraction, F in the lower equation, was conventionally regarded as localized at the body upon which the force acts, altogether independent of the intervening medium. We can hardly imagine a starker contrast. Evidently, the mathematical representation has failed to capture something significant in electrical action. If so, what will happen if we deliberately set out to bring the concepts of continuity and flow into our understanding of electricity? In fact, Faraday had already shown that we need to bring continuity into our electrical thinking. His researches, especially those of the 11th series, reveal that the medium which intervenes between two electrified bodies really does play a role in their mutual action. As we well know, electrically charged bodies tend to attract bodies that are oppositely electrified. But electrically charged bodies attract unelectrified bodies as well. For example, an inflated balloon, electrified by being rubbed against fabric, or, as we shall soon see, against hair, will cling to a wall. If you were ever enraptured by this marvel as a child, here is your chance to recapture that delight. Since what we just saw was an instance of attraction, it would seem that the charged balloon is somehow capable of producing an opposite state of electrification on the wall's surface. This phenomenon is called induction, and it would have been understood by most of Maxwell's readers as representing a redistribution of the electricity in the body under induction. In this drawing from a 19th century textbook, positive and negative electricities, originally distributed evenly throughout body AB, have migrated in opposite directions under the influence of positively charged body F. F thus corresponds to the balloon in our video, while AB would correspond to the wall. This separation of electricities, called polarization, was thought to be perfectly consistent with the doctrine of action at a distance, and accordingly, Standard electrical science taught that the charged body F exerted its attractive or repulsive power directly upon those electrical substances. Its attractive or repulsive effort was actualized at a distance. It did not have to be propagated or transmitted from F to AB. But Faraday's experiments, in effect, inserted a variety of materials between F, the electrified body, and AB, the body under induction. And he found that different media sustained the inductive action in different degrees. This could not possibly occur if the action were direct. Faraday surmised that the different materials were different also in their ability to conduct lines of force. The better their conduction of the lines from F to AB, he reasoned, the greater would be the polarization exhibited by AB. Maxwell sees that differing abilities to conduct lines of force in the electrical experiment would correspond to a reciprocal property in the fluid analogy, namely, differing degrees of resistance to the fluid's motion.
The fluid here is supposed to have no inertia, and this motion is opposed by the action of a force due to the resistance of a medium through which the fluid is supposed to flow.
Even as we bring over the attribute of contiguity from the fluid metaphor to interpret the phenomenon of induction, so too does Maxwell bring over the attribute of resistance drawn from the phenomenon to enrich the metaphor. This is the way metaphors and images work. They do not simply stand alongside one another, but reveal new aspects in each other, and in so doing, themselves evolve. Think of Homer's extended similes, or the ever-shifting image of light in the opening scene of Aeschylus's Agamemnon. But if Maxwell's attention is on resistance, why does he bother to mention that the fluid has no inertia? After all, the imaginary fluid was from the outset supposed to have none of the properties of ordinary fluids except incompressibility. So it was always assumed to have no inertia. I think the reason Maxwell calls attention to it here is that he has introduced force, which in Newtonian mechanics acts exclusively on quantities of matter, that is, on bodies endowed with inertia. In explicitly denying inertia to the fluid, while at the same time declaring it susceptible to a force, Maxwell is abandoning the framework of Newtonian physics. Remember that the fluid is an imaginary fluid, a fluid in thought, whose properties can be whatever is thinkable, whether they conform to Newtonian principles or not. Then, since Maxwell intends the fluid analogy to apply to electricity and magnetism, this seriously playful exercise is implicitly exploring whether the physics of electricity and magnetism may controvert the physics of mechanical bodies. If so, electrical science will not merely be a new science, it will represent a new kind of science. In 1873, Maxwell's Treatise on Electricity and Magnetism will go a long way towards exhibiting what the shape of that new science might be. Now, since the resistance that Maxwell has just introduced is opposed to the fluid's motion specifically, it ought to be zero when the motion is zero. And the simplest relation for which two quantities become zero together is proportionality. Accordingly, Maxwell invites us to suppose that each unit of fluid moving forward in its course with velocity v experiences a proportional resisting force, kv, where k is a constant of proportionality specific to the medium. Maxwell calls it the coefficient of resistance of the medium. With this in mind, Maxwell proves the following little theorem. In any tube of flow, pressure decreases continuously in the direction of flow. For, he argues, each tube of flow is a queue of units of fluid. And in order to move forward against resistance, each unit of fluid must be driven from behind by a pressure at least equal to that resistance. But as freshmen know from reading Pascal, pressure in a fluid acts in all directions. So the pressure acting on the rear face of any unit acts also on the front face of the unit immediately behind it. And so too for all the other units in the queue, as the drawing shows. Then, in order for some unit, say A, to move forward against resistance, the pressure on its rear face has to exceed that on its front face by kV, the measure of the resistance. That is, P sub A minus P sub B equals kV. And similarly, P sub B minus P sub C equals kV, and so on. Therefore, in any tube of flow, the pressure decreases continuously in the direction of flow at the rate of kV for every unit volume of fluid, QED. On the basis of this theorem, we may calculate the pressure produced in the fluid at any distance from a source of known strength. For we showed that a unit of fluid at radius r moves with velocity v equals n over 4 pi r squared, and therefore must experience a pressure difference, delta p, equal to k times the velocity, and extending over the whole increment of length, delta r, which that unit of fluid occupies. Therefore, delta p over delta r equals kv equals kn over 4 pi r squared. So if we add up all the delta p's associated with successive increments delta r along any tube of flow, from radius r to infinite radius, that amount will be the total difference between the pressure at radius r and the pressure at infinite distance, which we may assume to be zero. The art of taking such infinite sums is the integral calculus. Then we need only integrate the expression for delta p from r to infinity, which is especially easy since k, n, and 4 pi are all constants, and we obtain p equals kn over 4 pi times 1 over r. Thus, the pressure produced by a fluid source having strength n is inversely proportional to the distance r from the source, and similarly for a fluid sink, which is simply a negative source. Now, according to standard electrical theory, the electrical potential, commonly called voltage, in the vicinity of an electric charge is likewise inversely proportional to the distance from the charge. So Maxwell's physical analogy between the fluid velocity and the electrical force implies a parallel analogy between fluid pressure and electric potential. This is a truly important development because in a fluid flow problem, we can deduce virtually everything about it if we know the distribution of pressures. And similarly, in an electrostatic problem, Virtually all the information about it is implicitly contained in a mapping of the electric potential. This means that if two fluid configurations display the same distribution of pressures, they will be equivalent hydraulically, no matter how different they may appear to be in other particulars. And similarly, if two configurations of electric charge display the same distribution of potentials, they will be equivalent electrically, again, no matter how different they may be judged in other respects. Maxwell is about to make dramatic use of this fact. On the left, we see once again our single fluid source, now labeled F. And let us suppose that it pumps fluid into a surrounding medium having a coefficient of resistance K equal to 2. What will happen if we replace a portion AB of this medium with a new medium having coefficient K prime equal to 1? That is, a medium having less resistance. As you see in figure A on the right, the paths of flow tend to shift towards the region of easier passage, so that more lines occupy the region AB after the resistance is reduced than had occupied it originally. Now, the lines in these drawings represent tubes of fluid flow, but at the same time, in accordance with what we called the double-angled metaphorical vision, we are equally to think of them as representing electric lines of force passing from a charged body F through, say, air into some material body AB and back to air again. Then imagine you are an orthodox electrical theorist. What can you make of this picture? Certainly you have to dismiss the lines of force, since according to standard electrical doctrine, they have no physical significance. Then, poof! The lines of force are gone. That leaves you with nothing but the charged body F and the unelectrified body AB. But then you have to pronounce the diagram defective, since it fails to show the electrification, which you well know must develop on AB through induction by the charged body F. You will complain that the drawing ought to show little pluses and minuses clustered about the far and near faces of AB, as our earlier textbook diagram did. But Maxwell continues.
Construct the tubes of fluid motion, and wherever a unit tube enters either medium, place a unit source, and wherever it leaves it, place a unit sink.
That is what we have done in figure B. The portions of the former tubes that passed through the first medium are now independent tubes, having their own sources and sinks. Similarly, the portions occupying the medium AB now arise and terminate at their own sources and sinks. Maxwell then takes a third step, which we can understand if we remember the expression for pressure we deduced earlier. P equals Kn over 4 pi times 1 over R. You can see that the pressure produced by a source N at any distance R is not only inversely proportional to R, it is also directly proportional to Kn, the product of the resistance of the medium and the strength of the source. So in any medium with resistance K, suppose that every source N is replaced by a new source having strength Kn, while the medium itself is replaced with a new medium having resistance equal to 1. Then the numerator in this expression is unchanged. We merely understand it as the product of 1 and Kn, rather than the product of K and N. But that means the pressures are also unchanged. I have illustrated these steps in figure C. In the first medium, the source that formerly had strength 8 has now been multiplied by K equaling 2 to have strength 16. Accordingly, 16 lines now arise from the principal source F. Similarly, each of the 4 sources and sinks on the external surface of AB now has strength 2, so that 8 lines terminate on the near surface, and 8 lines arise from the far surface of AB. Finally, we suppose that the coefficient K, formerly equaling 2, is now made equal to 1. The numerator Kn in the expression for pressure is unchanged. Therefore, as Maxwell says, the pressures will remain the same as before. At this point, with beautiful understatement, Maxwell reveals what these transformations have accomplished.
We have now the original system of pressures produced in a uniform medium, so that the result is, in place of every external unit source on the surface, a source equal to K minus K prime.
This is what he means. Recall that in figure B, the sources and sinks on opposite sides of the boundary were equal. If they were combined, they would cancel each other out. But in figure C, every external terminus is double its internal partner. They cannot cancel. Thus, figure C is numerically equivalent to figure D. And then, since the pressures in D are the same as the original pressures in figure A, the two pressures A and D must be regarded as equivalent fluid systems. But to the extent that they also represent electrostatic configurations, with pressures corresponding to electric potentials, we must regard both representations as electrically equivalent too. So if, once again, you adopt the position of an orthodox electrician, you will once more dismiss the lines of force, but you will retain the sources and sinks, since they correspond to electrical charges, which you most certainly regard as genuine physical entities. The result of this will be the picture that now appears on the left, while that picture, in turn, is virtually identical to the standard depiction of induction on the right. It even displays the surface charges that formerly seemed to be missing from body AB. And therefore you will also have to admit that the standard textbook drawing is electrically identified to figure A, Maxwell's original case, which recognizes no surface charges, but bristles with lines of force. The concept of lines of force has effectively replaced the conventional notion of electric charge conceived as a substance. Now that we know the two representations are electrically equivalent, let us compare them rhetorically. The standard theory distinguishes sharply between bodies and the space between bodies, and it views electrification as the accumulation of electric substance on the surface of an electrified body. In contrast, Maxwell, following Faraday, conceives electrification as consisting in a state of the medium, possessing both intensity and direction, which is what the lines of force indicate. There is, moreover, no absolute distinction between bodies and space. Rather, both are regarded as mediating substances, which differ only in degree. Finally, Both interpretations are equally quantitative, so it makes no sense to dismiss one of them as unmathematical, as too many of Faraday's readers had done. Certainly a transformation like this one, with the equivalence it implies, delivers a formidable alternative to the favorite doctrine of the professed mathematicians. But to readers of Faraday, it will also carry a deeper significance, for such transformations of imagery are a Faradayan hallmark. Those of you who have read through some of Faraday's researches will have noted how self-effacing his narratives generally are. When Faraday uses images like pointing or conducting with respect to lines of force, he treats those images as though they were given by the phenomena themselves, not called up by his own poetic inventiveness. And when one image gives way to another, it is not because Faraday has deliberately transformed it, as Maxwell has just done, but because in a new experiment, the phenomena have revealed themselves with a new face. Such is Faraday's world, a world in which things are continually disclosing themselves. What they show of themselves is continually subject to transformation and replacement, for after all, we live in a world of change, and that changeableness includes our own understanding. But Faraday's world is one that is always ready to speak to us, and the fact of that constant conversation attests that the world is fit for us, a place where we are intellectually and discursively at home. Maxwell's world, I think, is more taciturn. It is by no means an alien world, but as an interlocutor, it is far less responsive than is Faraday's. In Maxwell's world, the phenomena do not clothe themselves in their own interpretive images. It is we who have to contrive the terms of expression. And once they are devised, it is we who have to assess and choose among them. Such is that process of simplification and reduction, which Maxwell named in one of our earlier passages. It is what Maxwell accomplished when he transformed the imagery of contiguous electrical induction into its seeming opposite, the imagery of action at a distance, thereby showing their equivalence. I wonder if the mobility of Faraday's images is one of the features that determined Maxwell to read Faraday before reading the mathematical theorists. Perhaps Maxwell found Faraday's expressive suppleness to be a potent corrective to that quantifying spirit which deals in fixed volumes and static symbols. I wonder if Maxwell ever wished that his own images could transfigure themselves the way Faraday's do. But perhaps by purposefully making those transformations on his own, as we have just seen him do, Maxwell comes as close as he can to Faraday's world. But is Faraday really so artless as it may seem I have made him out to be? Some readers might argue that Faraday's experimental abilities are surpassingly artful, and that it is precisely Faraday's practical expertise, not nature's readiness to speak, that we should thank for his illuminating discoveries. We need not insist upon either of these readings to the point of caricature. I am sure there is merit in both. But I do think it is worth noting that Faraday himself, in one of his annual lectures for young people, chose to characterize the world by quoting the very words in which Duke Senior commended the forest of Arden. Tongues in trees, books in the running brooks, sermons in stones, and good in everything. Well, you deserve to hear those lines recited by an abler voice than mine. Here is Tony Church in a 1978 BBC production of As You Like It.
Tongues in trees, books in the running brooks, sermons in stones, and good in everything.
Tongues, books, sermons, and good. It is features of Arden, not artfulness, which Faraday invited his young listeners to appreciate in the world. But if Faraday thinks we are in the forest of Arden, where, I wonder, in what Shakespearean forest might Maxwell say we are? Thank you.
Okay, we have a question. So I'm going to unmute you, and this will be our rhythm for as long as we're able to proceed this way. Please give your name and class, campus, and then your question.
Hi, I'm Rafi Rose. I'm a sophomore at Annapolis campus. And I was wondering what the difference in understanding is between the charge picture, the picture of individual charges on the inside, and the flow lines, and whether because I didn't understand if one was one was more able to evoke the idea of electricity to the audience, or if they were evoking different ideas.
Yeah, I think Maxwell has a kind of a double view of that. He makes a big point of saying that mathematically they're equivalent. So the big dispute between action at a distance and Faraday's and Maxwell's view isn't one that involves one of them being provable and the other being disprovable. But instead of, but the action at a distance view with the little charges on the surface, that forces us to believe that there is some kind of electrical substance. And it's paradoxical because it acts as though it was a body, yet it doesn't have any mass, and yet it can exert force and have forces exerted on it. Both Maxwell and Faraday feel that there's really very little to be said for that view, except people are trying desperately to hold on to Newtonian physics. And instead of that notion of ultimate reality consisting of discrete little pieces of substance, both he and Faraday have the idea that when we talk about electrification, we're not talking about something that's on the body. We're talking about a condition of the space between bodies, and that's a condition of tension, and instead of being discrete, it's continuous. In fact, in some places, Maxwell even Faraday suggests that it extends throughout the whole universe. It doesn't really have any boundaries, that the whole universe is knitted together by these conditions of tension, which we now call fields. But that was a kind of later terminology. So does that answer your question?
I guess to a certain extent. I'm wondering if the image with the charges was simply missing part of the image in the intermediary substance because it's not a vacuum, and maybe that's why it doesn't show that effect, because it seems like
Well, yeah, it's missing because according to standard electric teaching, which is that action at a distance idea. Nothing is supposed to be going on in the vacuum.
Okay.
Even if it's not a vacuum, the action at a distance people have a lot of trouble saying what they think is happening in the space in between.
Okay, thank you.
Sure.
Thank you. We have another question. Again, please introduce yourself. And hold on. Oh, let's see. I'm having an issue. There you go. Ms. Delaney?
Yes, thank you. My name is Sheba Delaney, and I'm a sophomore at the Annapolis campus, and I want to thank you for a really wonderful presentation.
So thank you.
Really, really a treat. But we've just read Bacon, so I've got Bacon on the brain, and I was really interested in the things that you presented about his ideas on method. And I was wondering if his idea of steering a course between being drawn aside and not carried beyond, would that be analogous to what Bacon is talking about in terms of anticipation and interpretation?
Yes, except I think Bacon regards those things as mistakes, and Faraday and Maxwell regard them as really a much more realistic picture of the way we actually think. What do you think?
I don't know if I'm still on the microphone. Thank you.
Yes, you are.
Okay, thank you so much.
Well, does that make sense to you? That
yeah, it does. I'm a little befuddled by this. Well, not exactly befuddled, but this idea of this imaginative approach. Is that an as if? Is it simply allowing the mind to look at the phenomena in front of it and conjecture about possibilities and then test to see which of those possibilities are true?
well, that sounds like Bacon. But the way I read Faraday, and I think it's pretty much the way Maxwell reads Faraday, is that nature and we are not really separate, and that nature shows itself without really our interference. We just the work we have to do to see nature in her true colors is to get out of the way. Now, sometimes that takes a lot of effort. It's difficult to get out of the way, but it seems to me that Faraday, at least the way I see him, couldn't be more different from Bacon, because for Bacon, you have to squeeze nature and, force her to do what she doesn't want. Maxwell, I think, is not that far in Faraday's direction. He thinks you do have to work, and I think he believes that we do have to use our own powers of conjecture and examination. But even he, I think, would not say that nature requires our forcing. I think he's much more in line with Faraday on that question than he would be with Bacon, I think.
Thank you.
Mr. Fisher, we got a written question. I don't know if you have that box open, but I'm wondering if I can ask, at risk of mispronouncing the name, Anurag Upadhyaya, to go ahead and ask the question. Are you
there's someone?
That person will need to unmute themselves. So why don't I'll just go ahead and read it. How important, and this is a junior from Annapolis, how important is the fluid model to Maxwell's artfulness? Is there conceivably some other model that could also analogically serve the same purpose at modeling the electromagnetic phenomena? Lastly, what necessity is it, if it is a necessity, that we concede to the principle nature conceals itself?
Well, let me go backwards in order of your question. I tried to suggest that for Maxwell, nature doesn't conceal herself, but we still have to use a degree of artfulness to figure out what she's saying. But when he comes up with the fluid model, I think he does so in a context that says we're not interested in the model as a model. And remember, he says, well, a physical hypothesis is not what we're after, at least not until we get very far along in our understanding. But we want to keep in touch with physical conceptions. And so I think that's the way he regards the fluid analogy. There's other analogies that he could have used, and he names a few of them. But the fluid analogy seems to be a way of giving us a vocabulary that allows us to think without committing us to categories that are so inflexible that our thinking gets caught in a rut. So, and I think in a couple of other of his writings, a wonderful paper that he wrote when he was, I think, 17 or 18. Anyway, embarrassingly young for the rest of us, called "Are There Real Analogies in Nature?" And that expresses similar ideas that we need a language in order to do thinking at all. But we tend to take languages so literally that only when we deliberately treat them as analogical can we steer that middle ground and, think fruitfully, but not dogmatically.
Thank you. I'm now going to pull up Will Thompson.
Hi, Mr. Thompson.
Hey, Mr. Fisher, I'm Will Thompson. I'm a senior at Santa Fe.
Yep.
And I guess I wanted to ask, so the whole analogy of electricity with, a field, that works as long as you imagine some sort of analogy to a medium, right?
Yes.
But, Einstein comes along and he says there can't be a medium, right? It can't exist in any inertial frame. After that, what is the fluid analogy of any help? Or are we left with this empty conception of some field that we've reified?
Well, I think that is a real problem for everybody. But when Einstein says there's no, I don't think he says there is no ether. I think he says we have no need to make a hypothesis of an ether. And in my opinion, that doesn't fundamentally disagree with Maxwell because, either in Maxwell's fluid analogy or what I take to be his interpretation of Faraday's notion of space, it's not a substance, at least it's not an inertial substance. And remember that moment when Maxwell says, well, the fluid doesn't have any inertia, but it's still subject to a force. I think he's saying, look, we are not constrained by Newtonian conceptions. And that's one of the advantages of an analogy. So I think what Einstein is denying is, in my opinion, something that Maxwell never really asserted. He certainly uses the word ether, but I think it has that kind of tentative status as merely a tool of thinking and not an assertion of being. Now that's the way I read him. Plenty of people don't read him that way. So read other people and see what they have to say.
Mr. Thompson, did you want to follow up at all?
I guess then what would it mean to say that something exists but isn't a substance? Or
Well, how about what is a substance? Answer me that one first.
I don't know.
Oh, so it does. See, if we can't say what a substance is, and I'm for the moment ruling out the literal meaning of substance, which is Aristotelian. But if we can't say what it is, then why should we treat it as the necessary category that all being has to conform to? So it seems to me, whether we use the word substance or ether or deny that we need anything at all, there's still this area in which our thinking just isn't completely clear, and we need to find a way of keeping that space open so that we don't fall into dogmatism. And that I think is one of Maxwell's aims in the particular paper that I was speaking about, the paper on Faraday's lines of force.
Okay, thank you, Mr. Thompson. We've had a hand up for a while from Katie Quinn. Are you there?
Yes, I am.
Okay, please introduce yourself and ask your question.
I'm Miss Quinn. I'm another sophomore from Annapolis. And when you had a slide that had the quote, "In any tube of flow, pressure decreases continuously in the direction of flow."
Mm-hmm.
So that made me think of Pascal and constant flow in freshman lab. And those two things seem to go against each other, those two ideas. But then I was thinking, maybe not. Maybe the force stopping constant flow is equal to the object stopping electrical current in Maxwell's idea of electrical fields or ether. So do you think that there is a disagreement there, or is it a similar idea and we're just returning to it 150 years later?
Well, I think there is a similar idea, but there's one enormous difference. The Pascal that we read in freshman lab is about static fluid, not flowing. So, Pascal would certainly not say that the fluid decreases in the direction of flow, because when there's no flow in the cases he treats of, and therefore the fluid is the same, at least at the same level. I think a more comparable author that we read might be Archimedes. Do I mean Archimedes? Yes, because there's that principle that the fluid tends to flow from regions of, how does he put it? He doesn't use the word pressure, but it would be what we would now call higher pressure to regions of lower pressure. And that's a version of Maxwell's little theorem, that the pressure decreases in the direction of flow. It's another way of saying fluid flows from regions of higher pressure to regions of lower pressure. And you had also asked about the application of that to electricity, but I've forgotten quite how you put it. So could you say it again?
Sure. So I was thinking that perhaps, because I was thinking of Pascal as talking about constant flow, which I guess is kind of a question. Am I just misremembering and it was static, not moving? And then I was trying to figure out how those two could go together. And I was thinking that perhaps the objects or forces that exert upon fluid that stop constant flow and change the way that fluid acts is similar perhaps to the objects in the diagram that, like the wall or something else, that stop the electrical arcs.
Yeah, And other people should join in here because I may be misremembering. The Pascal that I recall does not deal with flowing fluids at all. But if somebody can remind us about that, I'd appreciate it. But making the comparison to electricity, this is one of the things that I think makes Maxwell's analogy really hard to deal with, because the analogy of the flowing fluid is supposed to be analogous to static electricity. And I always have trouble dealing with that. But nonetheless, those are the terms of his analogy. And of course, you know, it makes us wonder, well, then what would be the analogy to current, which would seem to be moving fluid? Would that be accelerating fluid? Moving electricity would be accelerating fluid? Actually not, but that gets complicated. Maybe we'll save that for a bit.
Thank you, Ms. Quinn. Other questions? I don't see another hand up at the moment. There, we're going to hear from a tutor now. Mr. Bleichmar.
Sorry, am I on?
Yes.
You are.
So I'm Guillermo Bleichmar. I'm a tutor in Santa Fe. Thank you, Howard. That was wonderful, and I thought it was very moving to hear Maxwell's voice, and I'm curious about how you procured that. But I have a more conceptual question,
Sure.
which is about the role of thought experiments in Maxwell, and which seems like peculiar to him in a way that is different from Faraday. My experience of reading Faraday has less to do with thought experiments, and I wonder whether his reliance on thought experiments alters the sense that nature is speaking.
Yeah, and I think it's a nice observation that at least I would conjecture that Faraday doesn't use thought experiments because he doesn't need to. Nature speaks to him. I think Maxwell uses thought experiments because they are the one of those forms of imaginative thinking that we have to bear and we have to come up with for ourselves. But I'm also not sure of the dividing line between a thought experiment and analogical thought. They do seem to me somewhat different, but I'm not sure I could say exactly where the difference lies. Is that anything you see into?
Not immediately. What seems interesting to me about thought experiments, it's almost like you let imagination run, and then because you're following certain imaginary rules, it has real consequences. And I guess that happens with analogies too.
Yeah, some of Maxwell's thought experiments are wild indeed. There's one where he imagines that we have two charged bodies that are moving together with the speed of light, but they're also connected to wires that are connected to a galvanometer. And you know, how do you know which principles of nature to violate and which not to violate in something like that? So that's one of the reasons why thought experiment seems to me really hard to pin down.
Mm-hmm. Thank you. And could you tell us how you found that recording?
Remember, this was supposed to be a lecture delivered on April 1st. So a member of our community was very kind.
I thought I could detect that member of the community. I was kind of amazed. Thank you very much, Howard.
Certainly. By the way, I just wanted to remark that a number of sophomores from Annapolis have been here asking questions, and I'm delighted that people are interested in Maxwell even before they get to him in junior lab. So I'm just wondering what's happening in the sophomore year that is getting people interested in Maxwell. Anyway, whatever it is, keep it up.
I'm sure there's a good positive answer to that, but it might also be that you're the only game in town, Mr. Fisher. We do have another hand up here. Xiaodong Jin, are you there?
Can you hear me?
Yes.
Oh, great. Yeah. Hi, I'm Xiaodong Jin, and I'm a junior from Annapolis campus. And I guess my question might be a basic one because we are doing Maxwell right now in our lab class. And so when we read the paper on the analogies, and we see that Maxwell is making these analogies between like magnetism, electricity, and light. And it seems to me that, I'm not sure whether this is right, but it seems to me to be the same approach, almost like the second rule in Newton, that like the causes assigned to natural effects of the same kind must be so far as possible the same. So when I guess the confusion I had is that how do we know that this is the right approach to do it? Like maybe for me, I just kind of suspicious about what about we are making mistakes in the first step. How can we be sure that we can actually make analogies between, say, these kind of phenomenon and to draw further conclusions from that?
Yeah, I don't think we can. And I think that's one of the, that's actually, I think for Maxwell, a virtue of the analogies, that we remember that these are only analogies. We don't know how far they extend, and we can be sure that there is a limit to how far they extend. So we have less chance of falling into dogmatism if we remember that we're speaking analogically. But if someone says, well, why not just speak literally, which I think Newton means in that second rule. I don't think he has analogical thought in mind. I don't know what Maxwell would say, but I think what I would say is, yeah, if we ever get to the point where we really can speak literally, that's great. But we never quite know that we're there. And even when we think we're there, we might discover that our supposedly literal language wasn't as literal as we thought. And I think the action at a distance theories might be a good example of that. People thought that they were speaking literally when they spoke about centers of electric force, but maybe from a later point of view, that is Faraday's and Maxwell's, they weren't speaking literally. They were pulling over terms that they were used to from Newtonian physics, and really they were speaking analogically. They just didn't know it. So that's the best I can come up with.
Yeah, that makes sense. Thank you.
Thank you.
I recognize this name. We have another Mr. Fisher. Welcome.
Thank you, Mr. Sterling. And thank you, Mr. Fisher, for your very inspiring talk. I'm Eric Fisher. I'm a graduate of Annapolis class of '92. And I'm sort of pondering the question or questions you left us with having to do with artfulness and the representation or portrayal of nature. And my question dovetails a little bit with the previous exchange and the idea that action at a distance theorists aren't necessarily aware that they're speaking analogically. And so I want to invite you to say a little bit more about, if you wish to characterize the artfulness or lack thereof of these sort of three characters, action at a distance theorists, Maxwell and Faraday. And I'll just start off by provocatively suggesting that both Faraday and the action at a distance theorists seem to be examples of art that conceals itself for very different reasons. Faraday, I think, is interested in a certain type of moral relationship to nature or moral view of nature, whereas the action at a distance theorists seem to be unwitting. But you know, so I just wonder if you agree with that, and also how you would characterize Maxwell somehow as distinct from these two positions.
Yeah. Thanks for that great question. One of the discussions that I've had with a number of people for several decades, I think maybe 3 decades, has been Faraday's artfulness or non-artfulness. I have to confess, I have a somewhat romantic view of Faraday, and I really do tend to see him as artless, or at least more in that direction than the art that conceals itself. And part of the reason I feel that way about Faraday is that he comes from a religious tradition in which the reading of the Bible was thought to be kind of the paradigmatic artless reading. It's not at all the same as fundamentalism, most branches of which take biblical language as literal. So, you know, it doesn't take any art to discern it because it's literal language. That's not the way Faraday's group, they were called the Sandemanians, read it. But the way they tended to read the Bible was that it had images, but the images disclosed themselves progressively. So because you know, Faraday, I think, never really wrote much about his method of approaching nature. I'm not sure he would say he had a method, but since the religious tradition that he identified with was pretty articulate about biblical reading, that influences me in thinking that his approach to nature was probably similar. If we leave that out and simply look at his scientific writing, then I think to say it's art that conceals itself, you can make a good case, and many of my colleagues have. I think the best examples of the art that conceals itself are Faraday's lectures to young people. He gave them every year at Christmas time, and by the accounts that survived, they all went off without a hitch. And all of us who have ever tried to do experiments, whether before an audience or not, know that in order to get them to go off without a hitch, you have to work your head off. So it seems to me that's the place where people should go to find the Faraday who uses art that conceals itself. You know, I don't feel confident in speaking about the action at a distance people because I don't feel I have enough in in common with them, to know how they think. But again, Maxwell, I guess I keep, as I said before, I see him as a kind of middle figure. He knows that we have to use art. He is convinced that we have to use art. And it sometimes conceals itself, but I think on the whole, he's against that. I think he wants us to be aware of our own activities of simplification and reduction. In fact, that's a theme that I find in Maxwell a lot, is you don't ever do anything that you're not aware of. I don't know how deeply he holds that, but I just see it throughout his writings that scientific investigation has got to be self-aware. And the minute it isn't, we either fall into fantasy or we fall into dogma. And I think he really hates both of those things. But, you know, I asked that question, why did he want to read Faraday first? And I'm kind of intrigued by the notion that maybe he really likes the way Faraday's images seem to transform themselves. I mean, this is mere conjecture on my part. But, you know, Maxwell, the consummate mathematician, doesn't have to worry about mathematics leading him astray. So it's not the absence of mathematics in Faraday that draws him, I wouldn't think. So what is it? And that possibility about the images that work so differently from Maxwell's own images, I guess I'm just intrigued by the idea that exerts a kind of fascination for him, and that he doesn't really think we live in that world, but he can come pretty close. And that's why I asked the question, you know, if what forest would Maxwell put us in? And I invite any of you to suggest a Shakespearean forest. I have a couple of my own suggestions.
Mr. Eric Fisher, any follow-up?
Yes, I'm not sure if my microphone is still unmuted.
You are.
You're on.
Oh, okay. So yeah, just in response to your speculation about Maxwell's interest in reading Faraday, it seems that there are two possibilities that occur to me. One suggested directly from the lectures for children that you alluded to, that, you know, maybe there's something spellbinding about Faraday for Maxwell, and that Maxwell sort of is put into a childlike state when he reads Faraday. The other idea would be really different from that, and it would be that Maxwell approaches Faraday as one would approach the consummate artist to learn from.
Very interesting.
Thank you. Do we have any further questions? We can pause for a moment or two. I don't see any hands raised right now. And I'm checking the Q&A. Oh, I think, oh, here they come. Okay, I thought we might hear from Mr. Donahue. Are you there?
I am here.
Please proceed.
Okay, Bill Donahue, Santa Fe. And I have recently been reading a little passage from Maxwell's treatise that Mr. Fisher knows well, I'm sure, because I'm reading his comments on it. And it is on magnetism. He does the most bizarre thing to present magnetism, in that he and it's all imaginary as far as I know. He takes a magnet and he imagines a hollow in the middle of the magnet. And then he imagines a a little particle of magnetism, which he is very confident does not exist, that sits in the middle of this cavity. And then he does a whole mathematical argument that's built on this counterfactual. I don't know whether it's it can't be counterfactual because he's building his theory on it. But on the other hand, it's truly weird. And he ends up taking this cylindrical space that has the magnetic particle in it and making it infinitely thin, but infinitesimally thin, but infinitely broad, and then shows how that collapses a complicated formula into something simpler. And I can see that. I was wondering, well, why is he doing this? And I can see that, well, he's going to be drawing some things out of it later on. This is so un-Faradayan, and I'm wondering what is he up to here? You have any insights?
I wouldn't deign to call them insights, but I have a guess. It's not even a guess. I just want to point to a parallel. He does the very same thing with electricity. It's chapter 2, I think, of the second part, where he gives a complete analysis of Ampere's theory of electricity, which is a theory he doesn't believe in at all. Well, why does he do it? First of all, that was the current theory of Amperian attraction or repulsion between currents. So in a way, he had to address it in a textbook. But in the course of addressing it, he transforms it step by step to show that it is in every way equivalent to Faraday's theory, at least formally. So the very thing that he did in the paper that I highlighted in my talk, transforming one imagery, in this case, the lines of force, into the imagery of substantive charges. He did the same thing in the treatise with respect to electric currents. And I think that's what he's doing in this weird presentation of magnetism. He's starting from a substance-based theory and gets out of it concepts that work perfectly well in the theory he actually favors, which is the field theory, or the field based on lines of force. So I think that's why he does it. It takes an enormous amount of effort. And as far as I know, no university and no college, including St. John's College, ever studies that part of the treatise. But I guess I have one other thought about it. What do academic departments do instead? They look at all the theory that was erected about electrostatics, and it starts with the inverse square force, and then they look at magnetism and say, well, that's also an inverse square force, and then they say, well, look, all we have to do is erect a parallel. Everything we did for electrostatics, we can do for magnetism, and we skip over all the derivation. We don't need any of the fancy equations. We just bring all the concepts and theorems over. Well, Maxwell knew darn well he could have done that, and he didn't. Mm-hmm. So all I can think of is he thought it was important to make that journey. I almost want to call it a journey across the river Styx, from from the substantive theory of magnetism to the field theory of magnetism. But that's a guess on my part. What do you?
Mr. Donahue, any follow-up?
Yeah, yes, thank you. Yeah, I just wonder about that, whether Maxwell might be saying something about Faraday's approach to magnetism that it seems to him not quite possible to go from Faraday's view to the finished theory, and that you have to do something else in the course of it. I'm not quite sure if that's correct or not. But.
I think you're right, and that's a great suggestion, because the thing that Faraday doesn't have, he also doesn't have in the electric theory either. Faraday doesn't have the distinction between the magnetic induction and the magnetic field strength. The difference between H and B in Maxwell's terms. And he also, in his electrical theory, he doesn't have the distinction between electrical resultant intensity and electric displacement. So Maxwell has to get both of them, and you're right, he can't do it just from Faraday alone. So maybe that's an additional reason to start with substance, even though he's ultimately going to leave substance.
Thank you.
Thank you, Mr. Donahue. We have a couple of hands up, but I think I might interpose a written question that maybe has a briefer answer. So this is an anonymous attendee asks, and I recognize that you mentioned it, Mr. Fisher. What was the name of Faraday's religious group, and where can I learn more about the intersection of his faith and scientific beliefs? Any books, lectures, and so on?
They were called the Sandemanians, and there's a wonderful book by Jeffrey Cantor, C-A-N-T-O-R, called Michael Faraday, Sandemanian and Scientist.
Okay.
There's a couple of other things that will probably pop up online if you look up the Sandemanians. They're a very interesting bunch. And I must say, Cantor paints a very attractive picture of them, and I found it persuasive. So if you look it up, I hope you enjoy it. I think it's Cantor's book is a lovely book.
Thank you. Okay, so we have two hands up. These may be our last couple of questions. We'll see where things stand. So I'm going to pull up the first. Okay, Thomas Mulholland, I'm going to promote you to panelist because of the version of Zoom you're using. We'll see if this works. Are you able to?
Yes, I'm here.
Very good.
Yeah, I'm another Annapolis sophomore. And since the end of your lecture, I've been thinking about the question you almost jokingly posed about what forest Maxwell is in.
Mm-hmm.
And you've painted such a vivid picture of the world of Faraday and his almost childlike wisdom, sitting in Arden and learning from brooks and stones. I wonder, for those of us who don't quite have enough information on Maxwell, if you could maybe posit an answer to your own question and help us out and give us a picture of Maxwell's world as you see it?
Sure. Well, first of all, I would not say that Faraday's um, uh, spirit in the world was childlike. Remember, the person he quoted was Duke Senior, hardly a child. Um, uh, I would prefer the epithet artless rather than childlike for Faraday, because I think he has a very mature relation with the natural world. Um, my candidate for Maxwell's forest might be the forest outside of Athens in the Midsummer Night's Dream, because all the magic that has to be done. And maybe another candidate would be the forest on Prospero's Island, which again, requires a lot of work to make things happen. And I guess that's my picture of Maxwell too. He doesn't doubt for a minute that the world is intelligible, but I guess for Maxwell, nature does not speak quite as well, not at all as readily to us as the kind of nature that I feel is in Faraday. It's not that nature hides. It's not that nature needs to be forced, and it's certainly not that nature is alien. I think nature is, for Maxwell, ultimately intelligible. But just as I would say for Plato, the philosophic life is a life of great effort. It seems to me for Maxwell too, to put ourselves in a position where nature is as intelligible as he believes nature ultimately is. We have to exercise all sorts of arts. Some of them are experimental, and Maxwell did do experiments, but he admits himself he's not really that great an experimentalist. But in thinking of experiments, and this this touches on Eric's question about thought experiments. I think that kind of mental effort is something that Maxwell feels we simply can't do without. We would live in a world of fantasy if we stopped trying to turn over in our minds different languages, different concepts, different imagined experiments, and ultimately different physical experiments. I think for him, we have to do that constantly.
Thank you. There's one more hand raised, I believe, there.
Hi, I'm a junior from Annapolis. I had a question about your, when you said the inverse square law, the formula lose sight of something, and then the formula, you said the lose sight of the attraction of some sort. I wanted to hear more about what you meant.
Sure, I'd be glad to. And I'm really sorry to learn that there were so many interruptions in the broadcast portion. I think there must be a way to make that full presentation available online. So I'll try to see if there's a way we can do that. I'm sure we can.
I believe we will be able to.
Great. Okay, and I can transfer the recording that I have to the college to post it. Maxwell made this remark about I sort of his version of Scylla and Charybdis. Standard science tends to like to come up with physical hypotheses on the one hand, or to a mathematical formula on the other. And since before Newton, and certainly after Newton, either of those two things has been thought to be the primary fruit of a true science. And I think Maxwell is trying to say that whether they are fruits of science or not, they both tend to lead us astray. And the way the mathematical formula leads us astray is that it symbolizes only things that can be put into the form of a magnitude. And so if you're trying to understand attraction and repulsion, by the way, I think Newton almost expresses a similar attitude when he says, I'm not making hypotheses when I'm giving you the formula for gravitation. It's precisely the nature of attraction that the formula can't tell us. And even the word attraction, is that the right word? And we can look into the etymology of the word and see whether that really is well chosen or not. But a formula is not going to give us that kind of insight into the phenomenon. The formula is still good, and Maxwell uses plenty of them. But I think he wants to issue a caution along with every formula, just as he would issue a caution along with every physical hypothesis that we might make. That they can, what was this phrase? They can carry us beyond the truth. That's what the formula tends to do, or blind us to facts, which the physical hypothesis can do.
Right. Can I just add one more question?
Please.
So it seems like to me very similar to how Kant approaches the physical science, like finding a middle ground between the formula and the speculation, and then having this common ground in which comes about by necessity. But then we can think about the analogies as something that we construct. So I'm wondering which way of understanding the analogies is the more appropriate one. And is human understanding maybe only possible on this bridge or some sort of analogy that we create or come about by necessity?
Yeah, I'm going to need a lot of remindings about Kant with respect to analogies. But the thing that makes it hard for me to bring Kant into this conversation is that he is so ready to accept Newtonian physics on transcendental grounds. And it seems to me, if we put ourselves there, we have no need for analogies. I mean, analogies from that point of view might be some kind of psychological crutch to use temporarily. But it seems to me if we take the aim of transcendental analysis seriously, we will get we will get a science in a form that is far more secure in its foundation than anything that either Maxwell or Faraday are prepared to accept. and I know Maxwell studied Kant as an undergraduate, and Thomas Simpson has written to some extent on certain Kantian strains in Maxwell. But for myself, I feel that he left them behind, certainly by the time he wrote the treatise.
Mr. Fisher, I'm looking at the clock and we have one written question, and I think it would be a nice note to end on and hear your responses to. I want to give you the last word. So before I read it, I just want to thank you for taking this venture and being willing to do this. And I think it's been a lovely opportunity. I want to thank everyone who attended. And I think it's so wonderful that we have members of our Annapolis and Santa Fe student communities together for a question period, as well as alumni and other places, faculty from both campuses and others. So with those words of thanks, I'll let your reply to this question conclude our time. An anonymous question. I've been reading some of Maxwell's poetry recently, and I was wondering if you had any thoughts regarding what Maxwell's poetic inclinations might show us about his process. What is the relationship between mathematics and poetry? Coincidentally, many of his poems are set in nature, but more often mountainsides than woods.
That's lovely. And I would also like to say thank you to the whole community. I really enjoyed our conversation, even through this somewhat artificial, may I say, medium. Everybody has surely heard what I think ought to be, a kind of second motto for St. John's, is where we read the poetry of Goethe the science of Goethe and the poetry of Maxwell. I don't know too many examples of Maxwell's poetry, but the ones that I do all seem to me to have in common a great deal of witticism. I don't know that is indicative of his attitude towards poetry in general, but it seems to me wit and play are a very central part of Maxwell's scientific outlook. And I mean, it's serious play. It's the kind of play that leads him to conjecture that very weird thought experiment that I mentioned earlier in response to someone else's question, where he has two charged bodies moving at the speed of light and nonetheless connected to a galvanometer. I think analogy and metaphor for him have a playful element, and all of the finger-wagging remarks about don't get carried into dogmatism and don't get carried into fantasy. One can say that with in a very moralistic frame of mind and even a censorious frame of mind. But it seems to me mostly Maxwell says those things in a playful frame of mind. And I don't think it is overestimation to name playfulness and wit as a central element of Maxwell's science. You wouldn't know it from all of his writings, but even in the treatise, which is pretty sober, it bursts out every so often, and it's quite lovely when it does. So let me again say thank you to everyone, and I hope we can all enjoy many more lectures, and in not too long enjoy being together as a community in the same room as well as the same ether.
Thank you so much, Mr. Fisher.